So on to section three. Section three was the hardest part of this. I got a lot of messages from you people that said, "Sir, section three stinks. You're the worst teacher I've ever had in my life, and I don't want to do this. You're trying to kill me." And okay, well maybe I was trying to kill you by giving you the study guide, but I'm going to tell you what's going on with this section of of the study guide. There are a couple of different things that are going on. First, we're going to compare Pascal's principle to Archimedes' principle, and Pascal had to do with pressure, and Archimedes had to do with buoyant force. So when you go through this section, I love this first section of it. When you're comparing two ideas to one another, and I am definitely going to put this section on the test, every single bit of it, 1 through 8. And so I'm going to list it now, or tell you about it now, and maybe I will list it. So, number one, a person uses hydraulic brake to stop a car. Hydraulics are definitely about pressure being added, and the difference in the tubing, right? So you get this little bitty tube, and you force a bunch of fluid from that small tube to a larger opening, or vice versa, and you get some difference of pressure, right? So that's Pascal, right? So number one, if you're talking about pressure, you're talking about Pascal. Number two, I'll say 3, 4, 5, 6, 7, and 8. Number two, we're talking about something floating in water or sinking in water. Once you start talking about something floating or sinking, you're talking about Archimedes. Archimedes was the guy who ran around. Archimedes. Oh, I just spelled his name wrong. Archimedes. Oh, I think I was right the first time. I was right the first time. Worst speller in the world, Mr. Sokol. Not really, but close enough. And a fish uses his air bladder to float higher in water or move up and down in the water. Again, that's floating in water or moving up and down, changing the buoyant force. That is Archimedes. All right. So the next one says, squeezing one end of a balloon makes the other end larger. We're talking about pressure and changing pressure and going from smaller to larger. So pressure has to be Pascal. Anything that talks about pressure, we're talking about Pascal. A person feels lighter in water than on land. Obviously, that has to do with Archimedes. It's the buoyant force of the water. So Archimedes. Number 6, a camper pumps up an air mattress with a foot pump. So they're adding force to it. They're adding pressure. So we're talking about pressure. Therefore, we're talking about Pascal. I hope you're getting the idea. Number 7, obviously, rolling a toothpaste tube, adding more pressure to the tube. Therefore, we're talking about Pascal. Pressure is Pascal. All right, and buoyant force is Archimedes. And a scientist determines that the volume of an irregular object, he wants to find that volume of the object, so he sets it in water, and he notices the displacement of the water as the water goes up inside the beaker. Therefore, he's using Archimedes' principle. That's how Archimedes discovered the difference. Once he sat in his bathtub, he noticed the water level rose and flowed over the top of the bathtub, and eureka. So that's that quick section. I'm going to do the rest of the page. You're trying to install a 1 meter long bookshelf on a wall, and you want to make sure it's level. Well, this is where you use Pascal's principle, because the pressure pushing down of some sort of volume of water, you have that tube, right? So you stick water in the tube and you form it into a U. You can make sort of a cool little level with it, and that's how levels work. If you know construction at all, you see the bubble on the level. You set the level on it, and that bubble needs to go in between those lines to show that something is on a level surface. So if you use a tube and put some water in it so that the water will go up the sides of your U, and if the water level is at the same height on both sides, then you're going to have a level shelf. All right, so that's, you take water, you put it inside the tube, and you set it underneath the shelf, and you wait until the water level is at this exact same height. Now you have a level shelf. Number 10 was fun. I don't know if you know the difference between Lake Michigan and the ocean, but Lake Michigan obviously is freshwater as opposed to the Atlantic Ocean, which is saltwater. Okay, freshwater is less dense than is saltwater. Therefore, the paint spot, which is down right at water level in Lake Michigan, is actually going to be up higher once it arrives in port in Florida, because since it's in saltwater and saltwater is more dense, actually the ship is going to be raised up a little bit. Okay, and that's the answer to number 10. And last but certainly not least, now we have some math that we have to do. All right, and it says, what is the pressure in kilopascals exerted by a 23 meter column of fresh water, and how does this compare to standard air pressure in atmospheres? Now, you need to know a couple of things for this one, and you probably had to go to the text or use the internet to find those answers. I was hoping you wouldn't just go and jump right to the answer key that I'm sure you can find online somewhere. I was hoping that you could find two different things. One, pressure, big P equals density times height times gravity. And what you needed to know is that the density of water is 1,000 kilograms per volume. For 1 cubic meter. That was stated at one time in the book. I think I've mentioned it in passing, but I haven't really mentioned it over and over and over again, and we haven't talked about that for a long time. So there it is, and we'll move on. So now you multiply by the height, which is 23 meters high, and now we're at square meters, there we are. And I'm going to get to gravity, which is 9.8. And this is sort of an odd duck, because it's an acceleration, but we can notate it as newtons per kilogram, and everything shakes out exactly the same way. If I notate it as newtons per kilogram, I'm actually saying the same thing as saying meters a second squared, but that's just me using units to my advantage, because I want to get rid of this kilogram over here. And you would have seen it in the text, and I'm going to have you write it out like this, because if I give you a problem like this, I want you to be able to solve it. I'm not sure I want to do this one. It's not as crucial as some of the other stuff I'm going to have you do. Just to finish up, when you do this math, you end up with 225,000 basically 225,000, right, Pascal, or 225 kilopascal, and that's really where I want you to be, right? That's where I want you to end up. Why do I want you to be at 225 kilopascal? Is because when we convert to atmospheres, we're going to be talking about kilopascal, because one atmosphere is 101.3 kilopascals. And so if we have kilopascals here, and then we say, okay, well, I have 225 of these, and I divide by 101.3 kilopascal, then I'll have my answer easily enough. All right? And so there it is. You can do that math and you can tell me how many atmospheres there are.